If you think the universe is quiet right now, you're missing the noise. Subscribe because these 25 weird discoveries start harmless. Then they pile up into something that feels personal. In this video, we're counting down 25 strange things happening in our universe right now, and I'm going to show you the real science behind each one, plus the one pattern hiding underneath all of them. Let's be honest, space has always been strange. That's not new. What's new is how often we're catching the weird stuff in real time. Better telescopes, better sky surveys, better detectors, better computers. It's like we upgraded from a blurry security camera to 4K slow motion, and now we're noticing things we used to miss completely. And I want you to keep one thought in your head while we go through this list. The universe didn't suddenly become weird. We just finally got good at watching. 25. We are tracking something that shouldn't be here. Every so often, the solar system gets a visitor that did not grow up in this neighborhood. Not a normal comet from the Kuiper Belt, not a rock tossed from the asteroid belt, a true outsider on a path that doesn't loop back like a normal orbit. That's how we knew Oumuamua was different in 2017. That's how we knew Comet 2I, Borisov, was different in 2019. Their paths were hyperbolic, like a stone skipping across a pond and never coming back. Now, people online are watching another interstellar object that gets nicknamed 3I Atlas. The internet loves a dramatic name, but here's the solid part. If an object is truly interstellar, its speed and orbit shape will tell the story. It comes in fast, it doesn't settle into our system, and it leaves. That is why these objects make astronomers move, like someone just rang the doorbell at midnight, because time is not on our side. You might get weeks or months of good viewing, and then it's gone for good. That's why teams use every tool they can, ground telescopes, quick follow-up networks, and old survey data to reconstruct where it came from. This is also where big institutions quietly show up in the background. NASA's Jet Propulsion Laboratory loves tracking risky trajectories for missions, so the same kind of orbit math mindset applies here. And observatories like Keck in Hawaii are perfect for getting detailed spectra, meaning you can study what the object is made of based on how it absorbs light. And yes, Jupiter matters. Jupiter is basically the solar system's heavyweight. If a small object passes near Jupiter, gravity can bend its path. That can change where it leaves, how fast it leaves, and what we can predict. So when people say it might pass close to Jupiter, what they're really saying is a giant planet might grab the steering wheel for a second. That's science. Not aliens, not magic, gravity. But I'll admit something. Even without aliens, interstellar visitors still mess with your head, because they remind you our solar system is not sealed. It's not locked. Stuff can drift in from deep space, cut through, and leave before we even finish arguing about what it was. And that brings us to the next thing, because it's not a visitor from outside that's confusing scientists. It's something sitting inside our own galaxy that looks way too perfect. 24. We found a suspiciously perfect sphere hiding in the Milky Way. This one is real, wait, what? Material. Astronomers using radio telescope surveys in Australia spotted a faint shell in the Milky Way that looks almost like someone drew a circle in the sky with a compass. It's been nicknamed teleos, from the Greek idea of perfect or complete. And here's why that freaks people out a little. Space explosions are messy. When a star blows up, the debris runs into uneven gas and dust. It should warp. It should wobble. It should look lopsided. Even famous supernova remnants have jagged edges, knots, and clumps. But this thing looks unusually round. So the leading idea is still normal science. A supernova remnant, possibly from a white dwarf explosion, expanding into a region that was weirdly empty, and even so the shell stayed clean. That's the safe explanation, and it might be the right one. But even with that, there's a big problem. We don't know its distance well yet. And if you don't know the distance, you don't know the size. And if you don't know the size, you don't know the energy. So right now, Teleos sits in that annoying zone of astronomy, where you can say, this is probably this kind of object. But you can't yet say, and here's exactly how big it is, how old it is, and what it means. Radio astronomy is like that sometimes. You can see a ghost, but you can't immediately tell if it's a small ghost nearby or a giant ghost far away. And speaking of things that hit us like ghosts, there are particles slamming into Earth that carry so much energy we still don't know what fired them. 23. Something is launching ultra-high energy cosmic rays at us. Imagine a tiny particle, smaller than dust, hitting Earth with the energy of a well-thrown baseball. That sounds impossible, but it's the kind of comparison scientists use because the numbers are insane. These are ultra-high energy cosmic rays. They're usually protons or atomic nuclei. They travel close to the speed of light. And when they hit Earth's atmosphere, they smash into molecules and create a shower of secondary particles. We can detect those showers using huge ground observatories, like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah. Here's the part nobody likes. We don't know what launches the most extreme ones. Supernova remnants can accelerate particles, sure, but the top-end cosmic rays might need something more violent. People talk about jets from active galaxies, or the feeding zones around supermassive black holes, or neutron star smash-ups. But there's a catch. Cosmic rays are charged, so on their way here they get twisted around by magnetic fields. It's like trying to track where a ping pong ball came from after it bounced through a maze. So we get the punch, but not the return address. And that's why cosmic rays are one of those quiet mysteries. They don't come with a bright explosion you can point at. They just show up, hit our sky, and make us wonder what kind of engine is running out there. Now, if you want a hint about where some of those engines might be hiding, look at black holes, because they're turning up closer and more often than we expected. 22, black holes are turning up all around us. For a long time, black holes felt like rare monsters at the edge of imagination. Now they feel like a normal part of the universe's furniture. We know the Milky Way has Sagittarius A star at its center. We know other galaxies have even bigger ones. The Event Horizon Telescope made that very real for the public by giving us black hole images. But here's a newer kind of strange. Evidence suggests there may be a fairly massive black hole inside the Large Magellanic Cloud, one of the Milky Way's nearest neighbor galaxies. How do we even guess that? By watching stars that move too fast. When a star gets flung out at extreme speed, something heavy probably tossed it. One way that happens is a close encounter with a black hole. So researchers track the paths of fast stars and work backward like detectives. If multiple tracks point to the same region, you start to suspect a heavyweight. This matters because it means supermassive black holes might exist in nearby companion galaxies, not just in giant, faraway galaxies. It also matters because black holes are not just holes. They are movers. They shape star motion. They stir gas. They can kick stars out like a slingshot. And if black holes are this common, then the universe is more active than we used to picture. Which leads into the next strange thing, because the more active the universe is, the more people ask the big personal question: where does life fit? 21. We're rethinking how we search for alien life. For years, the plan was simple on paper. Find an Earth-like planet in the habitable zone. Find water, find life. The problem is that Earth-like planets are small and hard to read from far away. Their atmospheres are thin, their signals are faint. So scientists are widening the net. Instead of only hunting Earth twins, they're also studying worlds that might be easier to detect, like thick atmosphere ocean worlds, sometimes called Hycean-type planets. This is where the James Webb Space Telescope becomes the main character. Webb can study atmospheres by watching starlight pass through a planet's air during a transit. Certain gases absorb certain colors of light. So if you see a dip in the right pattern, you can guess what gases are there. And one idea scientists have been exploring is looking for methyl halides, gases like methyl chloride. On Earth, a lot of methyl halides come from life, especially microbes and ocean biology. That doesn't mean methyl halides equal aliens. Nature can do chemistry in weird ways. But here's the logic researchers at universities use, including groups connected to places like UC Riverside and the broader astrobiology community. If you find gases that are hard to keep around without a steady source, especially in combinations that don't make sense together, then you've got a target worth studying harder. Not proof, a clue, and the universe runs on clues. Now, The next one is a clue at the biggest scale possible. So big, it makes some people uncomfortable because it suggests the universe itself might have a preference. 20. The universe might be rotating like a giant wheel. This is one of those topics where you have to keep your feet on the ground because it can get dramatic fast. Some researchers have argued that when you look at large sets of galaxy images, you might find an imbalance in how many appear to rotate one direction versus the other. If the universe is truly random in that way, you'd expect the directions to balance out over huge numbers. If they don't, you have to ask why. But there's a giant danger here: bias. If your telescope system, your image processing, or your classification method nudges results in one direction, you can accidentally create a pattern that isn't real. That's why the next generation surveys matter so much, especially the Vera C. Rubin Observatory, which is built to scan the sky over and over with consistent methods. If there's a real large-scale pattern, Rubin's massive, clean data set should make it clearer. And if there isn't, Rubin should flatten it. Either way, it's a win, because we either discover something shocking about the universe, or we learn how our own tools trick us. And now, let's zoom from universe-scale ideas back down to something painfully clear: a planet dying right in front of us. 19. We're watching a planet get destroyed in real time. There are planets out there so close to their stars that the surface isn't just hot, it's melting. Some of these worlds are disintegrating planets, where rock turns to vapor and dust, and the planet leaves a tail like a comet. One of the newer famous examples is BD plus 054868, AB found using NASA's TESS mission. TESS works by watching dips in starlight. The planet passes in front of its star, the star dims slightly, and you detect that repeating pattern. But in this case, the transit looks weird because it's not just a clean planet silhouette. It's dusty material trailing behind, stretching the transit and deepening it. Think of it like this: instead of a solid marble passing in front of a flashlight, it's a marble that's crumbling into smoke while it moves. The orbit is extremely short, around a day and a bit, meaning it keeps getting roasted over and over. And researchers suggest it could be losing mass fast enough that, on cosmic timescales, it's basically in its final chapter. This is one of those discoveries that feels sad in a weird way. Not because we feel bad for a rock, but because it reminds you how fragile stable really is. Planets can be temporary. Now, if that gave you a sense of danger, let's talk about a planet much closer to home that looks like a warning sign. 18. We're going back to Venus. Venus is Earth's twin that took a wrong turn and never came back. Similar size, similar basic ingredients, but the surface is hot enough to melt lead. The pressure is crushing. The clouds are full of nasty chemistry. So why do we keep going back? Because Venus is the best lesson we have about how planets change. If we want to understand atmospheres, runaway greenhouse effects, and why some worlds become habitable and others become ovens, Venus is the perfect test case. NASA has missions planned like Da Vinci, designed to study Venus's atmosphere up close, and Veritas, designed to map the surface and look for clues about Venus's past, like whether it once had oceans and what kind of geology shaped it. Venus is important for another reason too. When astronomers find an exoplanet in the habitable zone, people get excited. But Venus teaches you that location isn't everything. History matters. Atmosphere matters. Bad luck matters. And if you want the universe to feel weird, just remember this: Earth and Venus started as neighbors, and one became home, and one became a furnace. Now, we've covered the first stretch of the list: interstellar visitors, a near-perfect shell in our galaxy, cosmic rays with no return address, black holes showing up nearby, a new way of searching for life, a possible universe-scale bias, a planet crumbling into dust, and a return trip to our solar system's harshest warning label. Next, we're going into the part where the universe starts feeling like it's hiding things on purpose. Dark matter-powered stars, fast radio bursts used like cosmic flashlights, a star that explodes twice, and why the moon might be full of tunnels big enough to protect whole cities. 17. The James Webb Space Telescope is hunting for dark matter stars. Dark matter is one of those words that makes people's brains split into two groups. Group 1, cool, science. Group 2, okay, so it's invisible ghost stuff? Here's the simple truth. We can see dark matter's gravity in how galaxies spin and how galaxy clusters bend light, but we still don't know what it is made of. Now, because scientists hate not knowing, they keep asking a sneaky question. If dark matter is real and it's everywhere, does it ever do times anything besides pull? One idea that keeps showing up in papers is something called dark stars, or dark matter powered stars. Sometimes people also talk about dark dwarfs. The basic concept is weird but easy to picture. A normal star shines because it's burning nuclear fuel in its core. But what if, in the early universe, a dense cloud of gas formed in a region packed with dark matter? If dark matter particles can collide with each other in certain ways, those collisions could release heat, not like fire, more like a slow, invisible heater. That heat could help a star-like object glow without normal fusion working the same way. Now, this is not confirmed. This is not NASA found a dark star. This is a theory with math that could be testable. And that's where the James Webb Space Telescope becomes important. Webb can look extremely far back in time, toward the first galaxies and the first star systems. If dark matter-powered objects exist, they might look different from normal stars. Different brightness, different colors, different heat patterns. So when you hear Webb is searching for dark matter stars, what it really means is scientists are using Webb to check if the early universe had objects that don't fit our normal star rules. And this is why it matters to the rest of the list. Because if dark matter can shape stars, even a little, it means dark matter isn't just background wallpaper. It's part of the story. And speaking of using weird space signals as tools, the next one is one of the coolest science hacks we've ever pulled off. 16. We're using fast radio bursts to find the universe's missing matter. For years, astronomers had an annoying problem. When they added up all the normal matter in the universe, stuff made of atoms, like stars, planets, gas clouds, they came up short. Like doing a full grocery count and realizing half your food is missing, but your kitchen is locked and nobody else has the key. So where's the missing matter? The leading idea, it's not missing, it's just hiding in faint, thin gas between galaxies. Hot, spread out, hard to see. Now here's the clever part. Fast radio bursts, or FRBs, are short blasts of radio waves from deep space. They last milliseconds. Blink and you miss it. Some repeat, some don't. And we're still figuring out what makes them, but many scientists think magnetars are a strong candidate. Even if you don't know what fires the burst is still useful, because when that radio signal travels across the universe, it passes through gas. And the gas slightly slows down different radio frequencies by different amounts. That effect is called dispersion. It's like a cosmic fingerprint of how much stuff the signal passed through. So if you measure the dispersion, and you also know how far away the FRB is, you can estimate how much gas is floating between galaxies along that path. This is where real institutions come into play. Arrays and surveys like CHIME in Canada help find a ton of FRBs. Other observatories and follow-up networks help pin down host galaxies and distances. It becomes teamwork across the planet, radio dishes, optical telescopes, data pipelines, and a lot of tired scientists staring at plots at 2 a.m. And step by step, FRBs have helped confirm that a big chunk of the universe's missing normal matter really is out there, floating in the space between galaxies. So yeah, the universe had missing matter, and we used a cosmic scream to find it. Now, keep that idea, because the next item is about a star that basically refuses to explode in a normal way. 15. Some stars explode twice. When most people imagine a supernova, they imagine one big boom. But in some cases, the story is more like boom, then boom. A double detonation is a proposed way a white dwarf can explode. A white dwarf is the leftover core of a star like our sun. Small, dense, and basically a cosmic ember that didn't fully die the dramatic way. If a white dwarf is in a binary system, it can steal gas from its companion. Over time, it piles that gas on its surface, like layers of powder. In a double detonation model, the surface layer ignites first. That first blast sends a shock wave inward, and the shock can trigger the core to detonate too. So it's like lighting a fuse on the outside that sets off the main charge inside. Why does this matter? Because type Ia supernovae are used as standard candles to measure cosmic distances. They helped lead to the discovery that the universe's expansion is accelerating work tied to observations across teams and institutions over decades, including data gathered by major telescopes and space observatories. So if some of those supernovae happen through double detonation, that affects how we model them, how we interpret their brightness, and how we use them to measure the universe. And here's the quiet human part of this. The iron in your blood, the calcium in your bones, those elements come from generations of stars living and dying. Supernovae aren't just fireworks. They are how the universe upgrades from simple atoms to the stuff that can become planets and people. So when scientists find evidence a star can explode twice, it's not just a cool detail. It's part of the recipe for us. Now let's come home for a second, because the next strange thing is right under our feet in space terms. 14. The moon may be hiding miles of lava tunnels. Most people picture the moon as a dusty ball with craters. But the moon has a secret. It has caves. Long ago, the moon had flowing lava, like rivers of molten rock. Sometimes lava flows form tubes. The outer layer cools and hardens into a roof, while the lava continues flowing underneath. When the lava drains away, it leaves a hollow tunnel behind. We've seen skylights, holes in the surface that look like entrances to these tubes. NASA's Lunar Reconnaissance Orbiter has helped spot features like this, and scientists talk about them because they're not just cool geology. They might be useful. If humans ever build a real base on the moon, one of the biggest problems is protection. Space radiation, micrometeorites, temperature swings that go from blazing hot to freezing cold. A lava tube gives you shielding for free. It's like the moon accidentally built underground bunkers before humans even existed. Now, are these tubes as gigantic as some people imagine? The size can vary. Some might be small, some might be big enough to hold huge structures. The point is, the safest place on the moon might not be the surface. It might be under it. And this connects to something deeper you'll notice across the whole list. A lot of the future of space isn't about finding shiny new worlds. It's about learning how to survive harsh ones. Which brings us to something that feels like science fiction but keeps showing up in real research. 13. Rogue planets might be building their own moons in the dark. A rogue planet is a planet that doesn't orbit a star. It's a world that got kicked out of its home system, or formed alone, or got tossed like a stray coin into the dark. No sunrise, no warm star, just cold space. So you'd think these planets are dead, boring, frozen lumps. But some observations and models suggest something surprising. A few rogue planets might have dusty disks around them. And a disk is important because disks are where moons and planets can form. If a rogue planet has a disk, it hints that it could be building baby moons, even without a star guiding the system. This kind of research gets discussed in astronomy departments in universities that study formation models, how disks behave, how dust clumps, how gravity builds structure even in harsh conditions. Now, I want to be careful. This is still an active area of research. Not every rogue planet has a disk. Not every disk means moons will form. But the fact we're even talking about it is wild. Because it suggests that the universe might be better at building structure than we give it credit for, even in the dark. And that takes us to the next planet in our own solar system, which has been confusing scientists for decades. 12. Uranus is leaking heat, but not like it should. If you line up the big planets, Jupiter, Saturn, Uranus, Neptune, you'd expect them all to leak some leftover heat from how they formed. These planets were born from violent collisions and heavy gravity squeezing them. That kind of formation should leave heat inside that slowly leaks out for billions of years. Jupiter and Saturn do this loudly. They emit more energy than they receive from the Sunday. Uranus, though, has been the weird one. Voyager 2 flew past Uranus in 1986, and the early picture made it seem like Uranus was basically not giving off much internal heat at all. For decades, that made Uranus look like the broken giant planet. But newer analysis and updated measurements suggest Uranus does release heat, just not much compared to Jupiter and Saturn. So now the question becomes, why is Uranus still the odd one out? One leading idea is that Uranus's extreme tilt is a clue. Uranus rotates on its side like it got knocked over. Some scientists think a giant impact long ago could have tipped it, mixed its interior, and changed how heat moves from inside to outside. So Uranus might not be cold because it's dead. It might be cold because its inside is arranged differently. And again, notice the theme. Planets look simple from far away, but they hide complicated interiors. And we're only now getting good enough data and good enough models to notice. Now we've hit number 12. And from here, the list starts leaning into big cosmic arguments, like whether our whole galaxy sits inside a giant void, why the universe's expansion rate doesn't match, depending on how you measure it, and why some signals we treat as sacred background noise might have extra clutter hiding inside. 11. The Milky Way might be trapped inside a gigantic void. Here's a problem that sounds small, until you realize it messes with the whole story of the universe. We measure how fast the universe is expanding in two main ways. One way looks at the nearby universe using things like supernovae and distance ladders that astronomers have built step by step. The other way looks at the early universe using the cosmic microwave background, that faint glow left over from the hot early days, mapped in crazy detail by missions like ESA's Planck. And here's the issue. Those two methods don't agree. The nearby method gives a faster expansion rate, the early universe method gives a slower one. This is what people call the Hubble tension. And no, it's not just scientists being dramatic. If both methods are solid, and they are, then something is missing in the middle. Now, one idea that keeps showing up is that we might live inside a region of space that's less dense than average, a kind of cosmic thin spot, a void. If our local area has fewer galaxies and less matter than typical, it could change how we interpret distances and speeds nearby. It could make the local expansion look a little faster from our point of view, even if the universe on the largest scale is doing something else. It's like standing inside a shallow dip and trying to measure the slope of the whole landscape, using only what you can see around your feet. Is that the final answer? Nobody can honestly say that yet. But the weird part is that we're now even considering this, because it means our address in the universe might be biasing our measurements. And if that's true, it's not just a math problem, it's a perspective problem. 10. We're catching planets at the baby stage. Most planets we study are ancient, old, settled. They've had billions of years to cool down, calm down, and stop acting like toddlers. But every now and then, we catch a planet so young, it's basically still in the messy stage, still hot, still forming, still figuring itself out. A really young transiting exoplanet is rare because you need the orbit to line up perfectly with us, and you need the data to be clean enough to confirm the pattern. And that's why this kind of discovery matters. Young planets are like time machines. They help us understand how planets form, how atmospheres build up or get stripped away, how orbits settle, and why some worlds become calm while others become chaos. It also reminds you that planet formation isn't a neat, quiet event. It's a long, noisy process. Stars form, disks form, dust clumps, gravity fights, everything. And somewhere in that mess, worlds are born. That's the part people forget when they look at a pretty space picture. Everything you love about the sky came from violence and mess. 9. Mars might be sitting on an ocean underground. Mars looks dead from above. Dry, dusty, cold, and basically allergic to liquid water on the surface. But below the surface, the story might be different. NASA's InSight lander did something simple but powerful. It listened. It measured Marsquakes. And the way the seismic waves traveled through the planet told scientists about layers beneath the crust. And some researchers have pointed to a zone where the waves slow down in a way that could match liquid, not rock, not empty space, something that behaves more like water. If that interpretation holds up, it suggests Mars could have a huge reservoir of water trapped underground. Now, is it a clean ocean like Earth's? No. It could be water in rock, like a soaked sponge deep underground. It could be salty. It could be trapped under pressure. It could be complicated. But even complicated water is still a massive deal, because water plus chemistry equals possibilities. And Mars is the one place in our neighborhood where that question, did life ever start, still feels like it might have a real answer. That's why people at places like NASA, JPL, keep pushing Mars missions. Because Mars isn't just a planet, it's a test of how common life might be. 8. Gamma rays we shouldn't be seeing reached us. Okay, this one is pure cosmic madness. In 2022, space lit up with one of the brightest gamma ray bursts ever recorded. Some people nicknamed it the boat, the brightest of all time. A gamma ray burst is what happens when something extremely violent happens far away, often tied to a massive star collapsing, forming a black hole, and firing jets of energy across space. These jets are so powerful, they can outshine whole galaxies for a moment. Now here's the weird part. Some detectors picked up extremely high energy photons linked to that event. Energies so high that, according to some models, they shouldn't travel that far without getting scattered or lost along the way. So scientists started asking, how did that energy make it to us? One idea that gets discussed is that there could be physics we haven't pinned down fully, like particles that can mix with light in special ways under certain conditions. You'll hear terms like axion-like particles in this conversation. These are hypothetical particles that show up in some theories and could help explain weird travel behavior for light over cosmic distances. Now, nobody is calling this solved. This is a frontier question. But it matters because gamma ray bursts aren't rare. They're a normal part of the universe's violence. So if one of the brightest bursts ever showed us something off, it might mean our picture of how light travels through the universe still has blind spots. And that leads perfectly into the next one, because it's about something much closer to home that also refuses to match our predictions. 7. Lunar landers keep finding only inches of dust. For decades, people expected the moon's surface to be buried in deep, soft dust. The logic seems simple. The moon has no thick atmosphere, no weather, no rivers, no forests. It's been sitting there, getting hit by micrometeorites for billions of years. So you'd think dust would pile up like snow in a place where it never melts. But when humans and robots actually touched the surface, the dust layer wasn't some terrifying sinkhole. It was there, sure, but not dozens of feet deep. So now the question is, why? Are impacts compacting the soil more than we thought? Is electrostatic charge making dust hop and move around? Are the old models just wrong? This isn't just trivia. It matters for the future. If you want to land heavy vehicles, build equipment, run rovers, and not choke everything in dust clouds, you need to understand lunar soil behavior. And it also matters because the moon is basically our practice arena. Before we try to live on Mars long term, we'll probably learn a lot by struggling on the moon first. 6. The moon is leaving us behind. This sounds like poetry, but it's a measurable fact. The moon is drifting away from Earth, very slowly, but steadily. And we know this because of one of the coolest simple experiments ever done. Apollo astronauts left reflectors on the moon. Scientists on Earth fire lasers at them, time the return, and measure the Earth-Moon distance with ridiculous precision. The result works out to roughly 1.5 inches per year. That's not fast in human life, but in deep time, it adds up, and it's happening because of tides. Earth's gravity raises tides on the moon, and the moon raises tides on Earth. Those tides act like a brake on Earth's rotation. Earth loses a tiny bit of spin energy, and that energy gets transferred to the moon's orbit, pushing it outward. So yes, the moon is slowly backing away, like a friend who's inching toward the door during a long conversation. Is it dangerous right now? No. But it's a reminder that even stable systems change. Earth and moon are not frozen in place. They're dancing, and the dance steps drift. 5. The universe is showing signs of self-organization. If the universe was born in chaos, why does it look arranged? When astronomers map galaxies, they don't see random sprinkles. They see filaments, walls, clusters, giant structures forming what people call the cosmic web. It looks almost like the universe grew nerves. Now, nobody is saying the universe is a brain. Relax. But the pattern is real. Gravity pulls matter together. And over billions of years, that pull forms structure. What's strange is how natural it looks, like it's following rules that create order out of randomness. And here's the deeper thought. We see self-organization in life all the time. Simple rules, repeated long enough, can create complex results. The universe might be doing the same thing, not because it wants to, because physics allows it. And once you accept that, you start seeing the next point even more clearly. 4. The universe is also evolving. Early universe chemistry was simple, mostly hydrogen and helium. No oxygen to breathe, no carbon chains, no rocky worlds. But stars are like cosmic factories. They fuse light elements into heavier ones. And when stars die, especially in supernovae, they spread those heavier elements out into space. That's how you get the materials for planets, oceans, atmospheres, life. So the universe didn't just expand, it matured. Each generation of stars leaves behind richer ingredients than the last. If you want a plain way to say it, the universe learned new tricks over time. And that brings us back to Jupiter for a second, because one of Jupiter's moons shows just how violent and alive a mature solar system can be. 3. Io is ejecting lava from a pit bigger than people can picture. Io is a moon of Jupiter, and it's the most volcanic world we know. Not one of, the most. And it's not because Io is special on its own. It's because Jupiter won't leave it alone. Io orbits so close to Jupiter that gravity squeezes it over and over like a stress ball. That squeezing makes heat inside Io, and that heat has to go somewhere, so it escapes through volcanoes, hundreds of them. The surface is constantly being resurfaced by lava, like the moon can't keep a stable face for long. Spacecraft and telescopes have watched hotspots there for years. Voyager first gave us the shock, Galileo gave us a deeper look, and newer infrared observations keep updating the story. When you hear about lava pits on Io that are enormous, the point isn't the exact size comparison. The point is this: there are places in our solar system where rock behaves like water, where the ground is basically never done boiling. And if that doesn't reset your idea of normal, the next one will, because it's not on Io. It's near Venus, and it's a safety problem. 2. We're tracking city killer asteroids hiding near Venus. There's a blind spot in our sky that makes astronomers nervous. Objects that orbit close to the sun, especially near Venus, can hide in the glare. From Earth, it's hard to see them because you're looking toward bright sunlight. And some studies and surveys have identified groups of asteroids sharing Venus's orbital neighborhood. If one of those objects shifts its orbit in the wrong way, it could become dangerous. Not end of the world, more like destroy a city dangerous. The scarier part is the warning time. If an asteroid lives mostly in the sun's glare, we might not see it until it's closer than we'd like. That's why this isn't just a telescope hobby topic. It's a planning topic. It's why scientists push for better surveys, better detection, and space-based infrared telescopes that can look closer to the sun's direction more safely than ground telescopes can. Because you don't want the first time you hear about a hidden asteroid to be on the news with a countdown clock. And now we reach number 1, the one that sounds like heresy to some people, but is being debated because data is getting so detailed that tiny leftovers start to matter. 1. The cosmic microwave background might not be pure. The cosmic microwave background, CMB, is often described as the leftover heat from the early universe. It's like an echo of the Big Bang, spread across the entire sky. We've mapped it with missions like COBE, WMAP, and Planck. And the map is one of the biggest foundations of modern cosmology. But here's the twist that keeps popping up in arguments and papers. What if a tiny part of that glow isn't only early universe heat? What if a small slice includes extra light from ancient galaxies, faint signals blended into the background? This wouldn't erase the Big Bang model. It wouldn't flip everything upside down overnight. But it would mean the background might have more clutter than we assume. And that clutter could affect ultra-precise measurements. And that matters because we're now in an era where tiny differences, tiny mismatches create big debates, like the Hubble tension we talked about earlier. So number one isn't the Big Bang is fake. Number one is the better we measure the universe, the more we realize the universe is not giving us clean, simple signals. It's giving us mixed signals. And that brings us to the real question we've been circling this whole time. If all these strange things are happening at once, interstellar visitors, perfect shells, cosmic rays with no address, nearby black holes, weird exoplanet deaths, Venus warnings, FRB, flashlights, moon tunnels, hidden asteroids, and a background glow that might be messier than expected, what's the challenge? It's this. We're collecting more data than ever, but the universe is not matching our old, neat stories. All right, so we've done the countdown. Now comes the hard part, because making a list of weird things is easy. The real problem is this. What do you do when the weird things don't stay in their own little boxes? Here's the challenge hiding behind the whole list. We built our understanding of space like a set of drawers. Comets go here, asteroids go here, planets go here, stars go here. Black holes go over there where they can't bother anyone. And for a long time, that worked. Mostly because our tools were limited. We didn't have enough clear data to see all the in-between stuff. Now we do. And the universe is basically telling us, yeah, your drawers don't fit the real world. That's the real tension behind all 25 items. Interstellar visitors blur the line between our system and not our system. Disintegrating planets blur the line between planet and comet tail. Rogue planets blur the line between planet and mini-solar system. FRBs blur the line between signal and tool. And even the cosmic microwave background, our most famous background signal, might not be as clean as we pretended. So what's the problem? It's not that the universe is suddenly broken. It's that our measurements are getting so good that tiny leftovers start to matter. And that creates three big headaches for scientists. Headache number one, we're drowning in data, but the data is messy. Headache number two, the most exciting signals are also the easiest to misunderstand. Headache number three, the universe loves to trick you with lookalikes. Let's talk about that third one, because it's the one that causes the most public chaos. A lookalike is when something normal pretends to be something wild. A dim galaxy can look like a strange early universe object if dust is blocking the light in a certain way. A natural chemical process can mimic a life gas signature if you don't understand the planet's chemistry. A weird orbit can look like an alien probe if you don't have enough data points yet. A measurement bias can look like the universe rotating if your survey method leans slightly without you noticing. This is why real scientists are often boring in public. Not because they hate fun, because the universe has embarrassed them before. If you've ever watched a NASA press conference, you'll notice the language is careful. People at NASA, JPL, ESA, and big university labs don't say proof unless they can defend it in a room full of angry experts. And it's not because they're scared of being wrong. It's because if you're wrong, you waste years of telescope time chasing a ghost. And telescope time is precious. Take the James Webb Space Telescope. It's one of the most powerful tools we've ever built, and every hour on Webb is like a golden ticket. So if a signal looks weird, you don't just point Webb at it and pray. You check it with other telescopes first. You check old data. You run models. You ask other teams to try to break your claim. The same thing happens on the ground. Keck Observatory in Hawaii can take spectra that help you figure out what something is made of. The European Southern Observatory has powerful instruments too. Radio groups can check if there's a signal in a different band. X-ray observatories can check if the object is blasting high energy. The point is, no single telescope gives you the truth by itself. Truth in astronomy is a group project. Now, here's where this gets more intense. The public wants one clean answer. Is it aliens? Is it a black hole? Is the universe spinning? Is there water on Mars? Is there life? And science almost never gives a one-word answer. It gives a probability. It gives best explanation so far. It gives, we need more data. That can feel annoying, but it's also the only reason we don't fool ourselves. Because the universe is full of things that look like other things. And we've reached a point where we have enough sensitivity to detect faint, rare, borderline cases, which is amazing. But it also means false alarms go up. Let's make it human. Imagine you're walking outside at night and you hear something in the bushes. If you have a cheap flashlight, you see nothing clearly, so you shrug and keep walking. If you have a powerful flashlight, you might catch 1,000 details, moving leaves, eye shine, shadows, and now your brain starts inventing stories. Better tools don't always make you calmer. They make you more aware of how much you didn't know. That's where we are in astronomy. And that brings us to the second big headache. The most exciting signals are also the easiest to misunderstand. Think about alien life searches. If Webb sees a gas in an atmosphere, that's not the same as seeing life. It's seeing chemistry. Sarah Seeger at MIT has talked for years about how biosignatures are tricky. You can get false positives. You can get weird planets with weird chemistry. You can get signals that look like life until you realize the planet is basically a chemical factory with no biology at all. So the challenge is not find a gas. The challenge is rule out everything else that can fake that gas. That's hard. And it's the same story with cosmic rays. You detect a particle shower. Great, but the path is scrambled. Great, so now you're looking for the source without a map. That's why teams build giant detectors and collect huge samples and try to find patterns in the statistics. They're basically trying to hear a melody in a crowd. And the same story hits the Hubble tension. You have top-level scientists, people like Adam Rees, Wendy Friedman, and others arguing about measurements, calibration, systematics, and how much trust to place in each step. That's not drama for fun. That's a real sign that we've hit the edge of precision. When the error bars get small, tiny disagreements become huge arguments. So what do scientists do when they hit this wall? They do two things at the same time. They improve the tools, and they improve the cross-checks. This is where the exploration part begins, because the exploration isn't just in space, it's in method. How do you stop the universe from fooling you? You stop trusting single clues. You look for multiple clues that agree, and you look for patterns that repeat. This is why the Vera C. Rubin Observatory matters so much. It's not just a telescope. It's a giant reality check machine. Rubin is designed to watch the same sky again and again, building a time lapse of the universe. That changes everything for things like interstellar visitors. You detect them earlier. You track them longer. Asteroids near Venus. You catch more of them and map their orbits better. Exploding stars. You see them at the start, not after the party is over. Variable galaxies. You watch them flicker, not just sit there. Rubin is basically going to turn space into a surveillance camera, ethically, for rocks and stars, not people. And when that happens, some of the strange things in our list will become less mysterious because we'll have context. A lot of space mystery comes from one problem. We only see one frame, one snapshot, but nature is a movie, not a photo. If you only see one frame of a person mid-step, you might think they're falling. If you see the whole clip, you realize they're dancing. Rubin gives us more of the clip, and Webb gives us deeper detail when we pick the right targets. Now let's bring this down to a few concrete examples, because this is where viewers start to feel the aha forming without you even saying it. Take that perfect sphere in the Milky Way. Right now, part of the weirdness is distance uncertainty. That's common with faint radio shells. So what do scientists do? They look for matching signals at other wavelengths. They look for related gas motions. They look for nearby star remnants. They search for clues that tell you whether the shell is in front of or behind certain features. Sometimes they use old Arecibo legacy data, if the region was ever scanned in that era. Sometimes they use modern arrays in Australia. Sometimes they combine it with optical and infrared surveys. The goal is to turn weird shape into weird shape with an origin story, because the origin story is the part that matters. Same with Mars. If InSight hints at deep water, nobody just declares ocean and moves on. They compare multiple quake events, They model rock types. They check if other explanations could slow seismic waves the same way. They look at gravity data. They look at magnetic history. They tie it back to Mars's surface history, riverbeds, minerals, polar caps. That's why NASA missions stack evidence like bricks, because any single brick can crack, but a wall holds. Same with the moon. The Apollo reflectors measure the moon drifting away. That's not a guess. That's a laser. That's math you can repeat. Then lunar orbiters map pits that could be lava tubes. Then researchers compare those features with lava tube formation on Earth. Then they model stability, temperature, radiation shielding. And suddenly, moon caves stops being a cool fact and becomes a serious plan. Now, here's the part that connects back to the whole list in a way people don't expect. The biggest weird thing happening right now might not be any single object. It might be the fact that we're seeing the universe as a system instead of a set of separate stories. When you watch enough data, you start noticing that the same basic forces show up everywhere. Gravity builds structure. Radiation reshapes surfaces. Magnetic fields scramble paths. Heat moves from inside to outside. And time turns calm things violent, and violent things calm. That's the universe's basic toolkit. And once you know the toolkit, you start asking a more dangerous question. What if a bunch of these strange things are not separate? What if they're different faces of the same deeper shift in our understanding? Because think about it. Interstellar visitors tell us space is full of travelers. FRBs tell us space is full of invisible gas. Cosmic rays tell us space is full of extreme accelerators. Black holes nearby tell us space is full of heavyweight engines. The cosmic web tells us matter organizes over time. So what's the pattern? It starts to look like the universe is not empty between the big objects. It's busy, it's active, and it's packed with stuff and forces we're only now learning to measure, which leads into the challenge that ties everything together. If space is that busy, then every measurement becomes harder because signals overlap, because backgrounds aren't clean, because noise is often real physics you haven't modeled yet. That's the uncomfortable truth behind the list. We are not just discovering new objects. We are discovering that the universe is harder to simplify than we hoped. And now I'm going to lay down the main question we're going to explore next. No big dramatic music, just a real question. If the universe is this active and this crowded, how many unknown unknowns are still hiding in our data right now? In other words, what are we already recording that we don't even recognize yet? That's where the next section goes. Because the way scientists answer that is by building smarter surveys, using multiple telescopes together, and hunting for repeating patterns that can't be brushed off as a one-time glitch. And the moment you understand how they do that, one of the items on the list, especially the interstellar visitor idea, starts to feel way bigger than it looked at first. So how do you stop the universe from fooling you? You treat every weird signal like a suspect in a lineup. And you don't let one witness decide the case. Because space is full of lookalikes. A comet can look like an asteroid if it's not actively gassing out when you spot it. An asteroid can look quiet until sunlight heats it just right and it starts leaking dust. A life gas can be made by chemistry if the planet is basically a pressure cooker. A perfect circle can be a real shell, or it can be your brain loving patterns and your data pipeline smoothing rough edges. So scientists do something that sounds boring, but is actually the whole game. They cross-check. You see something in visible light? You check infrared. You see a weird radio signal? You check optical. You see an X-ray flare? You check gamma rays. You think a star exploded? You check neutrino detectors and gravitational wave alerts if the event fits. This is why astronomy today feels less like a lone genius with a telescope and more like a global group chat. Webb sees an atmosphere hint. Someone else checks it with Hubble's old records. Keck gets a spectrum to confirm what the gas really might be. ESO instruments look at the same target from the southern sky. A radio array checks for signals in another band. Then people at universities start arguing politely in public and violently in private spreadsheets. That's not chaos. That's quality control. And the best part is, this method doesn't just solve mysteries. It also prevents fake mysteries from wasting years. Because if you don't cross-check, the universe will happily let you chase a mirage. Let's take the interstellar visitor idea again, because it's a perfect example of how this works in real life. When an object is first spotted, you usually don't know what it is. You just know it's moving. At first, you get a handful of observations. The orbit is rough, like trying to guess where a thrown ball will land after seeing it for half a second. With only a few points, you can get possible orbits. Some will look like normal comets. Some will look like oddballs. Some will look like they came from outside. So the early days are messy. That's why people online jump in immediately. They see uncertainty and they fill the gaps with imagination. But scientists fill gaps with more data. They pull in old sky surveys. They check if the object was accidentally captured earlier. They get more nights of tracking. They refine the orbit. And then you reach the moment where the orbit stops being maybe and starts being okay. We can call this, that's the calm part of the process. And here's the funny thing. A lot of the public thinks science is exciting because it's full of eureka, but the real excitement is often the opposite. It's when uncertainty shrinks. It's when a fuzzy story becomes a solid one. Now, the same cross-check mindset is what makes those big debates like the Hubble tension so serious. Because you're not arguing about one measurement. You're arguing about two whole ladders of evidence. One ladder uses nearby objects and builds distance step by step. The other uses the early universe glow mapped by missions like Planck and fits a whole model to it. Both ladders are made by careful people. Both ladders have been tested. So if they don't match, you don't assume one side is stupid. You assume the universe is hiding a trick in the middle. And the reason that's uncomfortable is because the middle might be new physics, or it might be something as annoying as a tiny systematic error that sits in the shadows of the method. This is why scientists obsess over calibration. Calibration is not sexy, but it's everything. It's like tuning a guitar. If your guitar is slightly off, every song is wrong, even if your fingers are perfect. Now, let's connect that to another item from the list, looking for life. People hear Webb detected this gas, and they want fireworks. But if you're serious, you go slow. You ask, what else makes that gas? Could volcanoes make it? Could sunlight break molecules and create it? Could the planet's surface chemistry fake it? Could the star's radiation be shaping the atmosphere in a way we don't see on Earth? This is why researchers like Sarah Seeger and others keep reminding people that biosignatures are not one gas. They're patterns. They're combinations that are hard to maintain without something constantly replenishing them. Because space is full of one-time events. A comet hit can add gases. A flare can change chemistry. A volcano can pump out a plume. So you want a signature that keeps showing up and makes sense over time. And that brings us to one of the biggest changes happening right now in space science. We're shifting from one-time snapshots to time-lapse universe. That's why Rubin is a big deal. Rubin isn't just going to show us new things, it's going to show us how things change. And when you see how things change, you stop being fooled by frozen moments. A mystery object becomes a moving story. A strange light curve becomes a repeating pattern. A weird flare becomes a known kind of event. Time is the missing ingredient in a lot of cosmic confusion. Now let's talk about something most people don't realize. Even background is not background anymore. When you say empty space, you picture nothing. But in reality, the space between galaxies contains thin gas, magnetic fields, and particles. It's not crowded like a city, but it's not empty like a vacuum bottle either. And fast radio bursts prove that in a very practical way. They became flashlights. We use them to weigh the invisible gas between galaxies. So now imagine what that does to your mindset as a scientist. If half the normal matter was hiding in faint gas, then you have to accept that the universe is full of invisible structure. Not dark matter invisible, just hard to see invisible. And once you accept that, you start treating every measurement differently because your signal has to travel through that invisible structure to reach you. Light is not just traveling through nothing. It's traveling through a medium. So when people say, why don't we trust one observation? This is why. The universe is not a clean room. It's a messy hallway. Now, let's bring this down to a very human kind of worry. Rocks. The city killer asteroids near Venus topic sounds like a movie, but the serious part is actually boring and practical. The scary part isn't that asteroids exist. The scary part is that some of them can hide in glare, and we only notice them late. So what do scientists do about it? They build better surveys, especially in infrared, because warm rocks glow in infrared, even when they're hard to see in visible light. NASA's planetary defense efforts lean heavily on this. That's why there's been so much interest in space-based infrared surveys and dedicated detection missions. Because if you can see the heat signature, you can see the rock earlier. Earlier means options, late means panic. And notice how that matches the theme of the whole video again. Better watching changes everything. We're not discovering danger because danger suddenly appeared. We're discovering danger because we're finally looking in the blind spots. Now, I want to widen the lens one more time, because we've talked about cross-checking, time-lapse surveys, calibration, and the universe being messy. Here's the deeper shift happening underneath all of it. Science is moving from single messenger to multi-messenger. For most of human history, we did astronomy with light. Now we do it with light, radio, infrared, X-rays, gamma rays, particles, gravity waves, and neutrinos. It's like the universe used to speak to us in one language. Now it speaks in 8. And when you hear 8 versions of the same story, you can catch lies, meaning you can catch errors, misunderstandings, and false signals. That's how you survive the modern era of weird discoveries. You don't argue with the universe using one tool. You build a whole toolbox. Now, here's the point where things start to connect emotionally, not just scientifically. Because if you're watching this as a person, not as a researcher, you might be thinking something like, okay, so is the universe just a giant mess? And the answer is yes and no. It's a mess in the sense that it's full of overlapping signals. But it's not a mess in the sense of being random. It's structured. Gravity makes patterns. Time makes cycles. Energy makes rules. And even chaos has habits. That's why the cosmic web exists. That's why galaxies form filaments. That's why stars live and die in predictable ways, most of the time. So the real question becomes, if the universe has rules, why are we seeing so many weird edge cases all at once? And here's the calm, honest answer. We're not seeing more weirdness. We're seeing more of the universe. We used to only hear the loudest instruments in the song. Now we're hearing the quiet ones too. And quiet instruments change the whole feel of the music. Now the next step in this story, and this is where we start approaching the key moment later, but we're not going there yet, is to look at how a few of these weird things might actually be related by the same hidden cause. Not aliens, not magic, just the same forces showing up in different costumes. For example, radiation. Radiation shows up as Venus becoming an oven over time, as atmospheres being stripped, as surface chemistry changing on icy moons, as signals getting altered across space, and as hazards for human exploration. Or gravity. Gravity shows up as rogue planets drifting alone, as black holes flinging stars, as Jupiter kneading Io into lava, as galaxies forming the cosmic web, and as the universe's expansion debate itself. So instead of treating the 25 items like a random list, we can treat them like 25 footprints left by a smaller number of forces. And when you see that, you realize something important. The universe isn't weird in 25 different ways. It's weird in a few big ways that repeat. And that's where the exploration gets serious. Because once you know which forces repeat, you can predict where the next weird thing will appear. And that's not just interesting, that's power. And here's the key moment. The moment where the whole list stops feeling like 25 random headlines and starts feeling like one connected message. It hits when you realize the weirdness isn't coming from one corner of space. It's coming from everywhere at once. From the space between galaxies, from the space between planets, from the space between the data points on a chart. For most of modern astronomy, we treated the universe like it had a clean stage and a few loud actors. Stars, planets, galaxies, black holes, everything else was background. A little static, a little fog. But now we're learning something that sounds obvious, yet changes everything. The background is not empty. The fog is not noise. The static is not harmless. The space between things is full of gas, thin enough to hide, but thick enough to matter, full of magnetic fields that can bend paths, twist signals, and erase return addresses, full of radiation that can rewrite chemistry on icy moons, strip atmospheres off small planets, and make a habitable zone feel like a joke if you don't understand the star. And the proof didn't arrive as one giant announcement. It arrived as a pile of small, annoying clues. Fast radio bursts turning into cosmic weighing scales, with projects like CHIME helping us realize that missing matter wasn't missing at all. It was spread out, faint, and sitting right where we weren't looking. Ultra-high energy cosmic rays, showing up like punches from a stranger, detected by places like the Pierre Auger Observatory, but scrambled by magnetic fields so badly we can't even point to the source with confidence. The cosmic microwave background, mapped by missions like Planck, giving us an early universe picture so precise that now we're arguing about tiny leftovers and tiny mismatches, like the universe is daring us to find what we missed, and then you stack the rest of the list on top. Interstellar visitors crossing our solar system like it's a hallway, reminding us we're not sealed off. If objects like Oumuamua and 2I, Borisov happened in our era of observing, then the galaxy has probably been tossing things around forever. We were just late to the party. A near perfect shell in the Milky Way that looks too neat, forcing us to admit that even explosions can look designed if they expand into the right environment. Black holes turning from rare monsters into common engines, especially now that tools like the Event Horizon Telescope made the idea public and real, and star motions keep hinting at heavy objects shaping neighborhoods of space. Exoplanets not behaving like tidy textbook dots, some crumbling into tails, some cooking, some forming fast, some dying fast, seen by missions like NASA's TESS that watch the sky like a patient security camera. Mars refusing to be a simple dead world, with InSight's seismic listening suggesting that the deep interior may still be holding onto surprises. The moon quietly changing the rules, with laser ranging from Apollo reflectors proving it's drifting away, and lunar orbiters mapping pits and tunnels that might decide where humans actually live when we go back. And Venus, the planet that sits right next to us like a warning sign, being targeted again by NASA missions like Da Vinci and Veritas, because we can't claim to understand habitability if we don't understand how a world becomes unlivable. Now, if you're paying attention, you see what all of this is really saying. The universe isn't giving us clean, separate mysteries. It's giving us one big message in 25 different costumes. Reality is more connected than our categories. The same forces show up again and again: gravity, radiation, magnetism, heat, time, and they keep producing edge cases that don't fit our simple labels. And that's when the weird becomes worse in a scientific way. Because once you accept that the space between things is active and the background is messy, a lot of our confident statements become less confident. Not because we were lying, because we were simplifying. And simplifying is fine, until your tools get good enough that the simplifications start breaking. That is exactly where we are right now. This is the era where we can finally see the faint stuff. And the faint stuff is changing the story. That's why the next decade matters so much. Because we're about to enter a time where we don't just discover new objects, we discover new context. A telescope like the Vera C Rubin Observatory doesn't just find a thing, it watches the sky change. It turns space into a time lapse. And time lapse is what kills fake mysteries and reveals real patterns. The James Webb Space Telescope doesn't just take pretty pictures. It pulls chemistry out of tiny shadows and tells us what atmospheres might be doing. Keck and the European Southern Observatory don't just look. They confirm, they test, they break claims, they tell us when we're fooling ourselves. And NASA teams at places like JPL don't just fly missions. They turn risk into data, and data into maps, and maps into better questions. So here's the key moment in plain language. We are learning that the universe is not quiet, and it's not clean, and it's not politely separated into topics. It's a living system of forces. And our instruments are finally sensitive enough to notice how tangled it really is. And once you see that, you can't unsee it. Because suddenly, the list isn't just strange things. It's a preview of what's coming next. More interstellar objects, because our surveys are improving. More hidden asteroids near the sun, because we're finally building better ways to look into the glare. More debates like the Hubble tension, because precision is climbing and the universe is refusing to be simple. More possible biosignature targets, and more false alarms too, because chemistry is tricky and stars can mess with the planet's air like a prank. More surprises under surfaces, on Mars, on the moon, on icy worlds, because the surface is often the least interesting part. And that leads us into the final truth behind this whole video. The universe hasn't become stranger. We became better listeners. We became better watchers. And the moment we upgraded our senses, we started hearing the parts of the universe we used to call silence. So if you felt, even for a second, like the universe is acting weird right now, you're not wrong. But the deeper truth is even more interesting. The universe is acting like it always has. We're just finally catching it in the act. And if there's one thing I want you to take away from this countdown, it's this. Every strange thing on the list is not a reason to panic. It's a reason to pay attention. Because attention is how mysteries turn into maps. Attention is how, what is that? Turns into, here's how it works. And attention is how we stop falling for lookalikes and start finding the real story. We're in the middle of a shift where astronomy stops being a collection of pretty facts and becomes a live feed of a changing universe. And that's why this matters. Not because it's spooky, because it's real. If you want the next video, click it now, because we're going deeper into the biggest unsolved mysteries behind these signals and which one discovery could flip our whole model of the universe next.